Dear colleagues, mostly noble gas isotope and gas research is directed to hydrogeology, and my background to this quite exciting expedition was that I was in 2022 a lecturer at a cruise ship, German cruise ship, and we visited Woodfjorden, and I had to prepare some lectures and found some open questions, because for me as a gas isotopic specialist and fluid specialist, I wonder, okay, this is exciting, the area, but not so much is done, and not all things are understood. And therefore, I asked one geologist in the Norwegian Polar Institute for an expedition. And this person contacted, now he is coming, Kim, and Kim says, okay, we do it. I have ordered a ship, a small vessel, and then we searched for some interested colleagues. And after half a year, we had a crew and interested scientists, and we made an expedition which was exciting for me. Yeah? Why exciting? Very different, not planned directions in science concentrated on an Arctic area was possible, and now we discuss not planned, quite interesting open questions. Okay, and for me, the interesting point is that the area in northwestern Svalbard is located not so far from mid-ocean ridge area. But this interaction is not so intensive discussed for. Why? Only the ocean geoscientists are concentrated at the ocean, and the field guys like us are concentrated on the continent. But in between is a gap. Yeah. Okay. So the second interesting point was for me that there are existing at this dimension also some large fault zones, and later we will learn which importance have fault zones for migration of fluids. This is the Woodfjorden fault here, which is very long and partly quite deep. I don't know if Sasha could tell us better than I am. It should be go deep to the Mohu or deeper, okay? And the next is that these faults are combined by active thermofluids and volcanic locations, quaternary in age. We know probably 1 million years old volcanic occurrences. Okay, now I come to the concept. It's uncommon. A lot of work we focused on Central and Western Europe. And in Central and Western Europe, we mapped the Eifel area in the Rhenish Massif, which has geological window to depth. This is Lacher See. Why? At Lacher See we have a lot of CO2, magmatic origin, and we see what the magma speaks now actual to us. Okay, the same is in the Massif Central. Then we mapped very detailed Bohemian Massif in Western Bohemia, the home of Kim, and Pannonian Basin too. And interesting is that that these three outcrops are of Voriscan origin related, and this outcrop is Carpathians origin related. Okay, what we learned by mapping is that this is the Eger Rift in Western Bohemia, here you see, and this is a profile we measured to learn what magmatic fluids do, which dimension the degassing has, and what is the peripheral part. We saw that we have in the 40 kilometers distance crustal degassing, then in between a mixture, and we have in diameter 10 to 20 kilometer in diameter a magmatic degassing, and in the lower crust there's existing active magma source. We learned it from monitoring research. And what we see in the profile is that the gas composition is changing. Here we have concentrated CO2, a high CO2 content, more than 99%, and very low nitrogen content. And this changes to periphery. Here we have a lot of nitrogen and very low CO2 content. And from gas flux, CO2 gas flux, we learned in the center of magmatic gas emanation, we have a very high gas flux, up to 30,000 tons of CO2 per year in an area of 2 square kilometers. And this is a degassing fault, which is highly active in fluids, in CO2-rich fluids. And we see a drop in the helium isotopic, these are helium isotopic ratio, a drop to the periphery, and also in carbon isotopes from -2 per mil to -17. Also here sees trend. Okay. Now we come to the area where we worked in the field. And here you see the situation at 2 sampling locations I collected. Jotun, this was a photo from Dahlmann monography, photo from 1997, and this was last year's situation, more or less the same. And this is Troll area, and this is complex D, and we collected here the primary center of outflow at this periphery, and this is a photo from last year. So, okay, go to noble isotopes. This is the lab of GFZ. The head of the lab is Samuel Niedermann. And the important point is that we have only 3 isotopes, helium-3 and helium-4. And we could differentiate a lot of origins, which you see here. To understand the big chance for helium isotopic research, I have to say that helium-3 is stemming from solar history of our system, and helium-4 is comes from decay of uranium and thorium. So we have 2 end members mostly, which make some different signatures in the mantle, in the crust, in the air. And so we could quite a lot things learn from these helium isotopic ratios. What is the link to characterize some reservoirs? This is a result from literature which they investigated worldwide subcontinental mantle xenolites, like our xenolites. And they find these ratios, which is R is the measured helium isotopic ratio, and RA is the atmospheric helium. And we divide each other, and there is a very good ratio, which is not so complicated. We hold a ratio for lithospheric continental mantle 6.1, and for MORP, mid-ocean ridge basalt, 8. Probably. And so we could differentiate these two reservoirs. And the crust is quite low. And the second possibility are 3 neon isotopes we see here. And the neon isotopes we could use to characterize also ocean island basaltic trends and discriminate between MORP and these trends and crustal trend we see here. And the third possibility is argon isotopic ratio, which you see also. So we have, using these noble isotopes, 3 possibilities to learn about the origin of fluids. And now I come to our work in the field. The problem was that I had to realize that there is only a small diffuse degassing there. And gas sampling needs time and was a little bit complicated because air is a big danger. If you got air, if air is coming into the tubes, then it makes change. Okay, what we saw, CO2 concentration in Jotun was 11, and in Troll was also 10, up to a little bit more. And what we saw also, it's nitrogen as the concentration was 77 or 76 up to 84%. This is a result which colleagues got in, I think, expedition in 2005 before, the same results. What we also repeated was the high helium ratio, which is a little bit unknown for magmatic degassing. Okay, how to collect samples? You see me here at the Lacher See. We use such glass vessels, and at the base we collect the gas which is migrating up by a funnel, and then the gas comes in, and we close 2 stopcocks here. Here is the situation at the Lacher See, and the gas composition is quite characteristic, is nearly pure CO2, 99.3%. And mostly